Hello everybody and welcome to another Bowtie Teacher video. Today I'm going to be giving my predictions for what I think is going to be coming up in the 2H paper for Edexcel IGCSE Maths January 2020. I couldn't have done this video without the help of some people in the comments. You know who you are, so thank you very much, and if you could please subscribe to this channel to help it grow, that would be awesome. Let's get started. So the way that I've tried to do this is increasing difficulty as you go through this, so the ones at the beginning of the video are the slightly easier ones and it progresses in difficulty as you go through. We're starting off with frequency tables, and as you know we have to multiply the first column, which we call x, by the frequency, and we multiply these all out to get the f times x like this. And we can use that information to work out the mean. So we would add up all of the fx column and divide it by the frequency column to tell us the mean. If we want to find out the mode, then we put the one that comes up the most. So in this case there's 8 threes, so 3 would be our mode. And for the median, what we need to do is we need to add up the frequencies. So 15, 25, 35, and we would add 1 and divide by 2. That would tell us the position of the middle value. So 35 plus 1 divided by 2 is 18. So we then do a sort of quick cumulative frequency in our heads. 4, 7, that's 11, 8, that's 19. So the 18th one would be in this group here. Okay, so the only difference with grouped frequency is that you have to add an extra column for the x, which is the midpoint of the class. So 0 to 10, you can average the two extremes, 0 and 10. 0 plus 10 divided by 2 will give you the 5. 10 plus 20 divided by 2 is 15. Just make sure you check every single one, because often they don't go up in the same amount each time. And then we could just do our f times x again like that. And when we get our medians and our means and our modes, we'll actually be putting the class, not individual values for that. Okay. Polygons is something that comes up a lot. So we remember that if we have a regular polygon, then the interior angle here, the exterior angle here, and the exterior is 360 divided by the number of sides. Often they'll give you a question where you're given this number here, so you have to rearrange this. So if that exterior angle is 20, for example, then we know that 20 is equal to 360 over n, and we can rearrange for the number of sides. Or they might give you the interior angle. Let's say they give you 160 here, then you can work with the interior angle formula, but it's much easier to work out the exterior, 180 minus 160, and do the exterior formula. If you have an irregular polygon, let's say you've got a 6-sided shape, and you can work out the interior sum, so all of them added together, the formula for that is number of sides minus 2 times 180. So for a 6-sided shape, that would be 6 minus 2, which is 4, times 180 is 720. So in a 6-sided shape, all of the angles inside will add up to 720, and if it's a regular, like hexagon, then you can actually divide this by the number of sides to find out each individual interior angle. Okay, so 720 divided by n, 720 divided by 6, and then you can work out each individual angle like that. Standard form, you have to be able to convert between normal numbers and standard form, and your calculator can help you with this. So if you have 1,630,000, then your calculator will actually do the standard form for you. If you go to Shift, Setup, Number Format, and choose Scientific Mode, and the number of digits, just put a 5 in there, it doesn't really matter. And when we put 1,630,000, it will tell us it's 1.63 times 10 to the 6. Okay, so Shift, Setup, Number Format, Scientific Mode if you want standard form, or normal if you want to come back out of that mode and select number 1. Okay, we'll go back to normal like that. So converting between them, your calculator will do that for you. And then you have the more difficult ones where they have something like, let's say 16 times 10 to the power of 16n. Okay, and they'll call this something like r, and they say, well, what is r to the power of 3 over 2, or something like that. So if this was a normal number like 16 times 10 to the 16, and we had to raise it to the power of 3 over 2, then we would do 16 to the 3 over 2 separately, and 10 to the 16 to the 3 over 2 like that. Okay, so 16 to the power of 3 over 2, we're going to square root it to get 4 and cube it to get 64, multiplied by 10 to the power of times 16 by 3 over 2, and we get 24. Alright, to put that into standard form, we would do 6.4. Okay, so we've got 6.4 times 10 to the 1 to get 64. So we're going to multiply those two together in the powers, and we would usually add 1 here. But because we've got 16n, like this, when we add 1 to the power, we can't add 24n plus 1 to get 25n. We have to do 24n plus 1. Okay, so just pretend that that n isn't there, and then do it as you would normally do it, and then put the n back in if you have to at the end, if you've got something like 64, and you have to put that into standard form. Set notation, if you have a and b, and you have to do anything with intersections, so a and b, that would be the and. We use the and operator for this, and if you have union b, we say or. So you can be a or b, that's anything in either of these circles. Alright, then we have something like not a, so this is not, and that means everything outside of a, and we sometimes have combinations like a and not b. That's how we read that one. So it has to be in a, but it can't be in b, so it would be this sort of section here. Okay, everything inside a, but it can't be contained within b. Alright, so where you get these more difficult combinations, especially with the triple ones, what it's best to do is to try and shade very lightly in these. Let's say it's C and D, and we want to put a third one in here, like maybe E, and we say we want the C union D and not E. Okay, so what we would do with this is we would take this separately. C union D would be everything in here, the union of C and D, okay, all of that there, but then it cannot be in E. So we would shade the outside of E, because not E means outside of E. So everything outside of E, you're shading outside of E like that. And where those two cross hatches overlap, if you like, that is where the actual shading happens. So the reason I've done that lightly is because you would rub out everything that's not relevant. So the ones within C or D but not E would be this stuff here, because it's in C or D but it cannot be in E. So it would be something like that. So this sort of combination hatching, if you like, where they overlap, that is the final shading that you actually want. Converting units, this is where we would have something like 525 centimeters cubed, and we have to turn that into meters cubed. And students think, well, there's 100 centimeters in a meter, so I'm going to divide by 100. But what's actually happening here is that you have a drawing of some centimeters cubed. Let's make a random set of numbers that will multiply to give 525. So we could have 52.5 times 10 times 1. When you multiply those together, they get 525. But it doesn't matter what those combinations are, as long as they multiply to give the original. So 10 centimeters and 1 centimeter. Now, if I draw that exact same thing again, but this time as meters, then 52.5 centimeters is 0.525 meters, 10 centimeters is 0.1 meters, and 1 centimeter is 0.01 meters. So you can see now that if you just divide by 100, you're only doing one of the sides. We need to do all three sides. So we're actually dividing by 100 cubed, or a million. So 0.525 times 0.1 times 0.01, that means we're dividing by 1 million. Okay, so we could do this on our calculators. 525 multiplied by 0.1 times 0.01, and we get 5.25 times 10 to the minus 4. So 0.000525. Okay? If we're converting something like 10 meters per second into kilometers per hour, for example, then we would treat this as, I kind of do it in a logical way going downwards, so 10 over 1,000 kilometers every second. Okay, so we've divided by 1,000 because 10 meters isn't very much in terms of kilometers, but seconds is very small compared to hours, so we're going to multiply by 60 to get this into kilometers per minute, and then times by another 60 to get it into kilometers per hour. Alright, so you just have to decide with the units. That helps you to decide whether you have to divide or times. And 10 meters per second is 36 kilometers per hour. So if you can remember one of these conversions, that will help you to decide whether your answer is actually valid or not, because some people get this wrong and they say 10 meters per second is 360,000 kilometers per hour, or they might say 0.0036 and things like this. So it helps you to decide if you're in the right ballpark. Okay, so you can use ratios to help you with this if you like, but it's a bit more in depth. It's easier to just decide using the units what you have to do, whether it's times or divide. Recurring decimals, where we have something like 0.56363363 like that, or it might just have the 3 with the 2 dots on top. What we do is we actually write this out as x equals like that, and then when you have 2 dots, you multiply x by 100. If you have 1 dot, you multiply by 10, and if you have 3 dots, you multiply by 1,000. So 2 dots, we have 100x. And what that does is it lines up all of the recurring decimals for us. So we times this by 100, we get 56.36363 like this. So you'll notice that all of these line up, starting from right to left. And then we get to a point where they don't line up anymore. So we're going to subtract these two, 99x, and we do 56.3 minus 0.5 gives us 55.8. Okay? So now we can divide through by 99, and we're not really allowed decimals in a fraction, so we can times everything by 10, 558 over 990, and see if this will cancel down on our calculators. 558 over 990 is 31 over 55. Okay, so you can check that on your SD button, 0.56363 like that. So you know you've got the answer correct. It usually asks you to show that, so you have to just go through this process of multiplying by the number of decimal. The number of dots is the number of digits that you multiply by. Okay, so if you're not sure about recurring decimals, you can practice these on your own. You're literally just making up a recurring decimal. I could do like 1.37 with a dot here, okay? And you just go through the process. You can check it on your calculator at the end and make sure that you've got the fraction that you said you would. With proportion, what we're looking at here is how two variables are linked together. It's usually x and y, but it can be other things as well. If we have a linear relationship between these two, then y is proportional to x. And the thing that links these two together is the gradient. Okay, so what we would do is we would say y and x are linked by, we just change this proportional sign to equals k. So the k is the gradient, and that is the link between y and x. As k gets bigger, y gets bigger, and so on. Okay, so we have to be aware of all of the different relationships that we can have between y and x. So it might be a squared relationship like that, or a cubed relationship would be a bit steeper perhaps. But what you would do is you read the question, it says y is proportional to x squared, or the square of x, or y is proportional to the cube of x, and we change the proportional sign to equals k. So y is equal to kx cubed. And we use the information in the question to work out what k is. So we can substitute for y and x and work out k. And then once we've done that, we just rewrite the formula with k. So let's say we had y is 20 when x is 2, so 2 squared. We would rearrange this for k, and we'd get 20 divided by 4 is 5. So we would rewrite this as y equals 5x squared. Okay, if we had something like y is 16 when x is 2, then we would write 2 cubed there, divide by 8, and we have k equals 2. So in this case, it would be y equals 2x cubed, and 2 is the constant of proportionality, as it's called, so the link between the two variables. Sometimes you have inverse proportion, so in that case, y is proportional to 1 over. And in this case, it might be 1 over x, or x squared, or the square root of x. Whatever it is, you just put that in the denominator. Okay, so we replace the proportional sign with equals k, and when we do that and multiply by 1 over, the k just goes on the top, and the x goes underneath. So if it's y is proportional to x squared, it becomes y equals k over x squared. Once you've understood this, the rest of the question is usually quite simple. You just have to find the information linking y and x. Usually they would say y equals something when x equals something, or they might have a table of values which link x and y, or they might even have the graph itself, and you have to read off your x and y from the graph. Alright? Rearrange it to find k, and then rewrite your equation once you've found k. Let's say it's 4, then you rewrite it like that for part A. And then for part B, they'll just give you another scenario, so they'll change y and change x and just ask you to find out what the new one is. So you just substitute in for this or rearrange it depending on what the question's asking. For sequences, we start with the basics where we have a sequence like 3, 7, 11, 15, etc. And in, say, year 8 and 9, we would just ask what's the difference between these two. 4, and that becomes the n, and then we do the 4 times table, and then say how do we get from the 4 times table back to our original, so we would subtract 1. For GCSE, they don't usually give you the sequence, they'll give you random bits of information like the third term is 11, and the fourth, well, let's do the fifth term is 19. And they say work out what the first term is, or work out the sum of the first 4 terms and things like this. So we can't use this 4n minus 1 anymore as it stands. What we need to do is to use the formula nth term is equal to a plus n minus 1d. Okay? The nth term is a plus n minus 1d. And the a is the first term, and the d is the common difference. The difference between the two numbers, consecutive numbers. Okay, so here the third term is 11. What we would do is we do 11 equals, because 11 is the term itself, and n is 3 because it's the third term. So we would write a plus n is 3, and d, the common difference, we don't know. 11 equals a plus 2d. And we're generating simultaneous equations because we have two unknowns, a and d. The fifth term, let's put it over here, is 19, is a plus, this time n is 5, and we can rewrite that as 19 equals a plus 4d. That's our second simultaneous equation, which we can then subtract these two to find the first term, which is 3. Sometimes they'll use the sum formula. So sum formula is n over 2. This is given to you in the front. 2a plus n minus 1d. And if you're not sure about the formula for nth term, you can see it kind of derives from here. From a onwards, that's the formula for nth term. So it's sort of contained there if you forget it. And let's say the first 4 terms are equal to 26, 36. So they might say in the question, let's say they say the 4th term is 15 and the sum of the first 4 terms is equal to 36. So now we still don't have a lot of information to work with here. We have to generate these simultaneous equations from the nth term formula and the sum formula. Okay, so the 4th term is 15, so we're going to say 15 equals a plus 4 minus 1d, where n is 4, so we get 15 is a plus 3d. That's our first simultaneous equation. And then our second one is to use the sum formula of 36 is equal to n over 2, so n is 4, so let's write that in there, 4 over 2, 2 lots of a, we still don't know a, and then 4 for n minus 1 times d. Okay, so we can clean this up a bit. We divide by 2 and we get 18 equals 2a plus 3d. This is our second simultaneous equations. So now we have our 2, we can just do our usual simultaneous equations using our doubling 1, tripling 1, or multiplying 1 by 3, subtracting them and all of that sort of stuff, using our calculators to check. But what we'll do is we'll find out a is equal to 3 and d is equal to 4. This is without knowing what this actual sequence was in the first place. And then they might say, well, what's the 20th term, or what's the sum of the first 10 terms? And you substitute all of those values back into the relevant equation that you need. Okay, so if you ever see any sequences, 99% of the time you're going to be generating simultaneous equations using the nth term and the sum formula. With circle theorems, what we do is the more difficult ones is where we have a chord, which is a line that joins 2 points on the circle, and that splits the circle into 2 sections, which we call segments. So this is called the minor segment, and this is called the major one because it's bigger. But when you're talking about these circle theorems, you're talking about angles in the same segment, or alternate segment theory, or things like this. And with the first one that we're going to do, we're making an angle inside the minor segment here. So that angle in there is contained within that minor segment. And then if we make another one and connect those two together, then these 2 angles are in the minor segment together. They're equal to each other. Okay. Similarly, these 2 in the major segment, they're in the same segment, so they're equal to each other as well. If we have a tangent coming across here, and we make a chord which goes into the tangent's point here, hopefully you can see that that chord has made another minor segment here, and the angle here is contained within that minor segment. So I can make any angle in the major segment that connects these 2 points on the chord, and this will be exactly the same as our one in the minor segment. So this is called the alternate segment theorem because one is in the minor and one is in the major. Okay. If I then go, let's say a different color here, and I go here, I've made a chord in the minor segment here, so this one will be the same as the blue one. Okay, so I hope that that you now understand the alternate segment theorem, because Edexcel like to ask this a lot because students don't really get it. So try to understand how this is built up, because sometimes they might have a cyclic quadrilateral like this, so you actually have to draw connections between the correct corners in order to use this theorem further. We also have this one where we have angles at the center and angles at the circumference. So this and this are related, they're double each other. So make sure you can word all of these in the correct way. And then we have intersecting chord theory, where we have two chords that overlap each other. And these sections, when you multiply them together, the same colored ones, they are equal to each other. So that A times B is equal to C times D. So if you've got two chords overlapping inside the circle, we use this formula. If the chords are outside of the circle when they overlap, okay, in this case, what we have is the whole of this line here multiplied by the outside section is equal to the whole of this line multiplied by this outside section here. Okay, so we have the whole line. So if we have A and B, then it's actually A plus B multiplied by B. Hopefully you can see that on there. And then you can use these to do some further work on the question. Usually it's an algebraic one or something like that, and you have to do some proofs. Completing the square is a useful tool for us, and the point of completing the square is that when you complete the square, it gives you the coordinates of the turning point of a quadratic. So they often ask you to put it in this form of x plus p squared plus q. They might have different letters, but essentially you've got a bracket squared and then a little remainder. That's what completing the square kind of looks like. And when you plot this graph, then the negative of p, so if it's minus 3, it will be plus 3, or if it's plus 7, it will be minus 7. So the negative of p is the x coordinate, that's the x coordinate, and the plus q, that's the y coordinate, and the sign of that stays the same. So the sign of the x is the opposite, but the one on the y stays the same. So if you have something like x minus 3 squared plus 4, then the turning point of this particular quadratic will be the opposite of negative 3, which is plus 3, and plus 4 on the y. Then the graph will go through there, and that's when its minimum point will be. So your quadratic will go up like that. Okay, so that's why it's useful for us, because sometimes they'll ask you to translate a quadratic and ask you like a vector of where this has gone from the normal y equals x squared graph. So let's say y equals x squared goes through 0, 0. Then this one would have been shifted 3 units to the right and 4 upwards. So some sort of column vector like that. Okay. Often they'll just have an actual equation like x squared plus 6x plus 3 and ask you to complete the square by putting it into this form. So in this case, what we do is we half the x term, so the one that's just got a single x, we half that and we put it in the brackets x plus 3 squared. And if I expand x plus 3 squared, what you'll notice is that you get x squared plus 3x plus another 3x, but we also get plus 9. We wanted the x squared plus 6x, but we've introduced an extra plus 9. So we always subtract, no matter what this is, even if it's a minus, we always subtract the number squared. Okay? So whatever's in here, we always subtract that squared. Okay? So don't get confused about, oh, is it a minus 3 squared and then you turn it into plus 9. You're always trying to subtract the extra bit that you've introduced. And then we've got the plus 3 that we originally had. So we can clean this up a bit, and x plus 3 squared minus 9 plus 3 is minus 6. So this graph would go through opposite of plus 3, negative 3, and negative 6. So it would go through that point there. If we have a coefficient in front of the x squared like a 2, so 2x squared plus 12x plus 5, then what we do is we take a 2 out as a factor before we do anything. We're just going to take 2 out as a factor plus 6x plus 2.5. And then we complete the square on the thing inside the large brackets. So we kind of pretend that those aren't there and we just do our normal quadratic completing the square on this. So x squared plus 6x, we're going to do x plus 3 squared minus 3 squared, and then we add the 2.5 that we had there. Okay, clean this up, we have x plus 3 squared minus 9 plus 2.5 is minus 6.5, and then we distribute the 2 at the end to get 2 brackets x plus 3 squared minus 2 times 6.5 is minus 13. Okay, now if we use our calculator with the normal quadratic function, then we can use this to complete the square for us. 2, 12, and 5. We get the two solutions to the equation if they exist, but if we keep going down, it says minimum of y equals x squared plus b, ax squared plus bx plus c. The x coordinate is minus 3, which is the opposite of the x1 there, and we go down again, we have minus 13, which gives us the y coordinate. Okay, so the calculator completes the square for us, and then if we have, sometimes we have something like 12x, let's say 5 plus 12x minus 2x squared. If you've got a negative in front of the x squared, it could be a negative 1, like negative x squared. We just take that out as a factor, and I usually write it in the form of ax squared plus bx plus c, just so we don't get confused there. So minus 2x squared minus 2 times negative 6 to get positive 12x, and then minus 2.5 to get my positive 5 there. So again, we just do the usual x minus 3 squared. We still minus, and we're still minusing 3 squared, and then subtracting 2.5, like that. Okay, so we get minus 2 brackets x minus 3 all squared, minus 9 minus 2.5 is minus 11.5, and if there's a negative, they usually ask you to write it the other way round. So if we have minus 2x minus 3 squared, and then minus 2 times minus 11.5 is plus 23, in the question they'll ask you to write the constant first and then the brackets, like that. Okay, so completing the square, it allows you to see the coordinates of the turning point of a quadratic. We can also use it to solve equations, but it's much easier to factorize or use a quadratic formula as well. Check my other videos if you're interested in that. Similar shapes, we're looking at ratios of the sides, and if you have something like 12 and 18, then what you would do is you would put the ratio 12 to 18 and try to get that in a 1 to 2 or 2 to 3 or whatever that is. So we divide by 6 and we get a 2 to 3 ratio, or a 1 to 1.5. Okay, so all of the lengths of the larger shape, let's call that B, are going to be 1.5 times the smaller one. So they might give you something like this, 20 on this one, and say, well, what's this line down here? So in this case, we would divide by 1.5, and if they have a 4 there, we would times by 1.5, depending on which direction we're going. Okay, because this is times 1.5 to get bigger, so we would divide by 1.5 if we want to get smaller. Okay, then they'll do something like, well, the area of A is 50 centimeters squared. What's the area of B? And students go, well, it's a 1.5 scale factor, so I just times it by 1.5 and I get 75. But when you have an area of something and I make it bigger, I'm actually multiplying the length by 1.5, two of the lengths. So I'm multiplying by 1.5 in one direction and then in the other direction as well. So I'm multiplying by 1.5 squared. Okay, so when we're looking at this is the length of A to the length of B. When we're looking at the area of A to the area of B, we have to square the scale factor. So I'm going to take this one here just because it's nicer numbers. 2 squared is 4 and 3 squared is 9. Okay, So when we're doing the area scale factor and this smaller one is 50, we're trying to find out what the larger one is. To go from 50 to 4, we have to divide these two and we get 12.5. So to go from 9 to the larger one, we have to times 12.5 there. Alternatively, you can just do 50 times the scale factor in its lowest form, which was 1.5 squared. Depends on how you like to deal with these ratios. But you get the scale factor and you square it, then you can either times by 1.5 squared or divide by 1.5 squared. And then they might have the volume. Let's say the volume of A is 100 centimeters cubed. Then we would do 100 times 1.5 cubed now, because we've gone in 3 dimensions, so we've now got to times another 1.5, and we work that out. Or we can say the volume of A to the volume of B is, instead of 2 to 3 or 4 to 9, we're now doing the cube, so 2 cubed to 27, 3 cubed, okay? And we can do our ratios like this. 100, what do I multiply 8 by to get 100? What do I multiply? Do the same on the other side. Okay? So this is how we manipulate the volumes and the areas, because sometimes they give you the area scale factor to start with, and students just work out what the difference between these two is, or 9 divided by 4, but that is the square of the length scale factor. Okay? So if they give you the information in areas and you divide them, you then have to square root them to get the length scale factor, and then you cube that to get the volume scale factor. All right. So if they give you the area, divide them and then square root them to get the length, and then cube it to get the volume. All right. And similar shapes is a topic where they don't really say it in the question, like these two shapes are similar. They kind of superimpose them on top of each other. So I've drawn some examples here of some common ones where they sort of, you can see the two triangles are inside each other like that. So you separate them out into their two separate ones like that. It's usually a lot easier to do these questions. So you've got your pentagons and you've got them next to each other side by side. It's a lot easier to then think of this as similar shapes. And a frustum, this was in the 1HR paper. You can separate a frustum, which is a cone with the tip removed, into two separate cones. So the top one is the smaller one, and then the larger one is the original one without it removed. So you can start to work with this. These are actually similar shapes. So sometimes it's not easy to spot, especially if you have two triangles on top of each other but flipped upside down. They would be similar to each other.